Hi, this is Dr. Bay, and here's Bugsy. And today we're going to talk about the first part of SN2 mechanisms. We'll delve into reaction kinetics, arrow pushing, transition states, and stereochemistry. So stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
A nucleophilic substitution is a type of reaction in which one nucleophile replaces a leaving group at a tetravalent sp3 hybridized carbon atom. There are two mechanisms for nucleophilic substitution that you're going to learn about in this course. The difference between the two mechanisms lies in the timing of the bond breaking and bond forming steps. The first mechanism that we're going to go over is called SN2. Now, if we break down what this stands for, the S stands for substitution, while the N stands for nucleophilic, and the number 2 is because this reaction is bimolecular and two species or molecules are involved in the rate determining step, which we'll get into details in a bit. For now, let's go over the basics of the SN2 mechanism. Remember that in any reaction mechanism, molecules must collide in order to react. Some collisions are productive while others are not. The SN2 reaction is a concerted or one-step mechanism. In this reaction, the nucleophile attacks the carbon attached to a leaving group and the leaving group leaves. Highlighted in yellow is called an alkyl halide because it is an alkane molecule with a halogen bonded to it. In an SN2 reaction, alkyl halides, shown in yellow, act as what are called electrophiles, or sometimes you'll see it written as E+. If you break up the word electrophile, it literally means electron loving because the molecule itself is electron poor and it really wants electrons. Shown in green is what's called the leaving group, or LG. A leaving group is a component of an electrophile, and it typically is either an atom or group of atoms that can break off a molecule and still be stable on its own. Halogens in general are good leaving groups, but we'll discuss in further detail on what makes a good leaving group in the next video. Shown in pink is the nucleophile, which when broken down means nucleus loving. Nucleophiles are typically electron-rich, and they want to donate their electrons to an electrophile. So to quickly summarize an SN2 reaction, the three main components are that the nucleophile attacks the electrophile and the leaving group leaves. Note that an SN2 reaction is a direct displacement of a leaving group with a nucleophile, but the two red arrows drawn show that this reaction is a one-step reaction, meaning the nucleophile attacks at the same time the leaving group leaves. But why? Both the nucleophile and the electrophile are involved in the rate determining step, which is why the reaction is SN2. An important concept to understand is that SN2 occurs by a backside attack, where the nucleophile approaches 180 degrees away from the leaving group. And this phenomenon can be depicted in what's called a transition state. It's the state at which there is a simultaneous bond breaking and bond forming signified by dashed lines shown in red. But the oxygen atom and bromine atom both have a partial negative charge at the transition state. In order for these two negative charges to avoid repelling, they must be as far apart as possible, which would mean 180 degrees apart. Transition states are normally drawn with brackets and a double dagger symbol written in the upper right-hand corner of the bracket. Let's talk about geometry changes throughout an SN2 reaction. The carbon in your electrophile has a tetrahedral geometry since it has 4 atoms bonded to it. As the nucleophile begins to attack, and this reaction reaches the transition state, the geometry changes to trigonal bipyramidal. And finally, as the leaving group leaves, the geometry goes back to tetrahedral in the final product. We can plot the structures of an SN2 mechanism on what's called a reaction coordinate diagram that essentially displays how much energy of a reaction requires in order to form the products. The x-axis shows the reaction progress, while the y-axis shows energy. On the left, we start the curve at our reactants, which would be our nucleophile HO-, plus our electrophile CH3Br. From here, it takes a certain amount of energy called activation energy to reach the transition state. Activation energy can also be written as E sub A. Then, from the transition state, the reaction goes to the formation of the product as the leaving group fully leaves. The amount of energy between reactants and products is the Gibbs free energy, delta G, or enthalpy, delta H. Lastly, if the leaving group of an electrophile undergoing an SN2 reaction was bound to a chiral center, there would be an inversion of stereochemistry. Keep in mind that this only occurs if the leaving group itself was bound to a chiral center. If there are other chiral centers in the other parts of the molecule that are not part of the reaction, they would be unaffected. To understand this better, let's look at an example. Draw the arrow pushing and transition state structure of the following reaction. So first, our nucleophile, NC-, would attack the carbon of the electrophile, and then the leaving group will leave. Notice that this molecule, 2-chlorobutane, has a chiral center of R. Now in the transition state, we're going to draw both the nucleophile, CN, and the leaving group, CL, 180 degrees apart from one another. Since neither bond is completely broken or formed, we have to draw their bonds as dashed bonds as shown in red. Then, in the final product, we form S2-cyanobutane, where the chirality has inverted. In summary, the SN2 reaction is a concerted or one-step mechanism where the nucleophile attacks the carbon at which the leaving group is attached to, and then the leaving group leaves. Just to reiterate, SN2 is the direct displacement of a leaving group with a nucleophile. In our next video, we're going to discuss what makes a good nucleophile and what are the best types of electrophiles specifically for SN2 reactions. See you then!
Organic.